Hi everyone, just waiting for everyone to join the session before starting. Just waiting a couple of seconds. Okay, hi everyone. I'm Celine Cato-Gilbert, and I will be chairing this session. I'm a hydrological forecasting scientist at NIWA. A couple of housekeeping notes. If you have any questions, please do use the live Q&A, which will be on the box on the right of your screen. If you have any technical difficulties, please use the red live support button on the top right corner. The session will go for about an hour and it will really end promptly at 12:45, and so we have to keep on schedule. But if the questions aren't answered, they'll be on the live Q&A, and so Hilary might be able to answer them later as well. So I'm very pleased to introduce Dr. Hilary Oliver, who will be discussing his work on the development of the open source Silk workflow engine. Scaling, it's all, well, quite a lot about the workflow. Hilary is a senior research software engineer at the National Institute of Water and Atmospheric Research in Wellington. He holds a PhD in astrophysical sciences, computational plasma physics from Princeton University. And he now works on software infrastructure for climate, weather, and weather-driven environmental forecasting systems. And in particular, workflow orchestrations for cycling systems. He's also the co-chair of the technical advisory group of the Unified Model Partnership, which is an institution that uses the Metaverse Unified Model around the world. So with all this in mind, I'm really pleased to introduce Hilary. Hilary, it's now up to you.
Thank you, Celine, for the introduction. Hi, everyone, all the invisible people out there. And unfortunately, I wasn't able to make last year's conference, so it's good to have a crack at it again this year. And I would like to thank the team at NeSI who've put this all together on this amazing virtual platform. They've been super helpful. So if I screw this up now, it's on me. By the way, I've noticed everyone's high-tech Zoom backgrounds of lovely beaches and the like. And as you can see, I've gone completely low-tech. That's actually a real plant behind me. So I'm going to try to share my screen now. Let's see if it works. Choose the right window. And to maximize that. Hopefully that's worked.
I can see your screen, Hilary.
Brilliant, thanks, Celine. So it was both a pleasure and a surprise to be invited to speak at the New Zealand Fish Scaling Expo. Mostly a surprise, to be honest. So I had this genius idea to pretend I'd got the wrong conference and work it until people felt really uncomfortable because this is a keynote and I thought I'd better try something different. But actually that's a really bad idea, so I'm going to skip the next slide, just pretend you haven't seen it. The 45-minute virtual drinks keynote was a much better idea, but I couldn't figure out how to play lounge jazz through my Zoom headset. So we'll just have to get on with the real thing. Right, so Celine said I lead the development of the Silk workflow engine, which originated at NIWA about 10 years ago. So to suit my biases, as well as the conference theme of scaling, I'm going to try to convince you that scaling really is all about workflow. Toward the end of the presentation, I thought it might be interesting for this audience to stretch the brief a bit and talk about my experience of scaling Silk up from a one-person research project to a production system with a small international team working on it every day. So here we go. First, a bit of background so you can understand some of the upcoming diagrams. So Silk allows you to construct and run distributed application workflows, which can be represented by a little graph like this. Each node in the graph is a task, which represents an application that runs on a computer somewhere, any executable basically. And the arrows or graph edges represent dependencies. For maximum flexibility, Silk works with abstract dependencies as opposed to explicit data dependencies. Here's a little glimpse of the DSL we use for defining these graphs in Silk. Basically, you just draw the graph in text form with arrows between task names. The graph diagrams don't really show the nuances of task triggering. The default is a task will trigger if the upstream dependency succeeds, but you can also trigger off job submission and fail and start of execution, finish, custom messages, and conditional expressions. So Silk started as a small research project on how to manage cycling workflows more efficiently. And when we went into production at NIWA in 2010, we had to manage this early version of our weather and environmental forecasting system. The red tasks in there are large atmospheric model runs, and they drive downstream sub-workflows for sea state, storm surge, and river flow. Our current system looks very different to this, but back in the day, this pretty much maxed out our aging HPC, and it seemed very complicated to the small team who had to manage it at the time. It is actually worse than it looks there due to its cycling nature, which I'll come back to later. Anyway, in around 2012, after NIWA had open sourced the Silk project, the UK Met Office adopted Silk. And by 2015 or so, we were having to manage workflows that look more like this. So you can see a bit of scaling coming to the fore here already. And now in 2020, this is a modern global weather prediction workflow from the UK implemented in Silk, which I'm just slowly zooming in on. You can forget about trying to manage anything like this with a bunch of ad hoc scripts instead of a real workflow engine. And eventually we'll get to the point where we can see what the individual tasks are. Right about there. Those blue ones happen to be instances of the forecast model. So I think you can see from this already that workflow orchestration is absolutely a scaling mechanism. It can greatly amplify the scale and the complexity of the work that you could otherwise do. Interestingly, my colleague Alec Spletzer suggested yesterday it might be helpful to think of a hierarchy of scaling like this, from program subunits to modules, packages, shared libraries, programs, parallel programs, and application workflows at the very top. And I think that is actually a valid way to look at things if you think of each level sort of including what comes below it. So within application workflows, you can of course have huge parallel programs which scale in their own ways as single tasks. So those are the places around the world that we know of that use Silk at the moment. Our biggest site remains the UK Met Office, which is one of the world's largest and most important global forecasting centres for weather and climate. And the Met Office has used Silk 24/7 in research and production since early 2014. As you can see there, in February this year, I was told they had reached about 12 million HP jobs per month, and 99.6% of them were managed via Silk. So you'll notice all my headings are rectangular without regard to word boundaries, because I think they look cool. It takes a little bit of effort to read them. So that says where to get info on Silk. So this presentation isn't my usual introduction to Silk, so I'm trying to focus mostly on things scaling related. So I'll start with a pointer to more information in case anyone wants to follow up on it. First port of call should be the silk.org website, which looks like this. Let's go back to the slide. The front page of the website explains it all, including why another workflow engine. You can download Silk releases there, read the user guide, access our discourse support forum, and even follow a link to get commercial support from Altair, the PBS people, PBS Pro for Silk. We also published, got a big paper published in Computing and Science and Engineering just last year on workflow automation for cycling systems. Lots of good information in there. However, I'm going to start by touching on the traditional meaning of scaling as I understand it in the computational physical sciences, because that does actually provide an amusing segue into workflow. And besides, I happen to have a background in Physics, the one true science. Well, last century, in the 1990s, I was doing a PhD in plasma physics in the US, and the Cray C90, pictured here, was the actual machine I was using, the last flagship vector machine at the National Energy Research Supercomputing Center in the US. Now, people have been playing around with early parallel machines for quite a while at this point, but the massively parallel processing revolution hadn't hit yet, and Cray was still fabricating these custom fast vector processors. And as far as I recall, scaling wasn't really a hot topic in the real world at that stage. We just tried to make our models run efficiently on these big single core systems. But by the time I came back to New Zealand in late '99, NIWA had just got the first supercomputer in this country. It was a Cray T3E MPP machine, massively parallel processing, built from commodity processors and fast interconnects. And this one, Coupe, with 144 cores and peak performance of about 168 gigaflops, was truly a step change in our computing capability here. Now, it's tiny by today's standards, but it briefly held the 64th position in the world top 500 list when NIWA purchased it. Top of the list today is this thing in Japan, Fugaku. 7 million CPU cores, 28 megawatts of power to run it, $1 billion US, and at peak performance of 415 petaflops, which I think means 415,000 trillion floating point operations per second, which is staggering. So anyway, what is usually meant by scaling in scientific computing in the MPP era, to me, is getting massively parallel scientific models to scale efficiently over as many processors as possible on huge machines like this. Now, if you're into this sort of thing, you'll be aware of Amdahl's law, which says for a fixed problem size, parallel scaling is strongly limited by the serial fraction of your code. Luckily, most of us don't have a fixed problem size, though, and Gustafson's law says that scaling is actually linear if the problem size can be scaled up with the resources by increasing the model resolution, for example. That's because the parallel part scales with the resources, but the serial part remains the same size. So I'm not going to say much more about this sort of scaling, but I just want to mention one prominent example of it as a natural lead into silk style workflow scaling. So this example is that says to NGMs. So NIWA is a core member, core partner in the UK Memphis Unified Model Consortium, which has embarked on a once-in-a-generation rewrite of their atmospheric model, the unified model, to make the so-called next-generation modeling system, NGMs. One of the primary reasons for this huge, decade-long, 170 FTE plus effort is that the unified model, which has actually done a remarkable job despite starting life in the pre-MPP era, doesn't scale well enough for next generation exascale HPC hardware. One of the reasons for that is in the UM's spherical coordinate system, which you see on the right there, the coordinates are singular at the poles, and that causes numerical problems at higher resolutions. Amusingly, the virtual spacing of model grid points near the poles can be smaller than the physical spacing of HPC cabinets that hold them. Anyway, the new model with this cube sphere grid in early testing has scaled to 160,000 cores. It's far better than what the UM can do. But let's say, in terms of workflow, what do you get for your 170 plus FTE effort? I wanted to have a sort of cartoon fail noise here, but again, I couldn't figure out how to play it through my headset. Anyway, give me a break. That isn't scaling. I was generous enough too to add gratuitous pre and post processing tasks so I could even call it a workflow. I'm going to have to apologize to my UK colleagues for this later. This is scaling. Now, a handful of those dots are your puny exascale model. So I rest my case, scaling is all about the workflow. But seriously, workflow orchestration really is at the heart of good utilization of massive HPC resources because you won't be running your massive models all of the time. And processing the output of these huge models typically involves staggering numbers of small jobs. And it's hard to use that much machine effectively by submitting all those jobs manually. You need some serious automation. And finally, MPP scaling is actually not all that matters for a real-world application of these models often, and workflow gets its foot in the door again here. I'm just checking my timing. I think I'm doing all right. It's good.
You've got plenty of time, Hilary.
But I've got plenty of slides to come. So, why are weather workflows so horrible? Well, thanks for asking. There are two main reasons. One of them is cycling, which I will come back to, and one is model ensembles. So the thing about model ensembles is atmospheric dynamics is super sensitive to initial conditions, and there's nowhere enough observational data to nail them down. So the state of the art is not actually to run one model as big as you can scale it, but rather it's to run an ensemble of many smaller models, each initialized slightly differently within the bounds of the observational and model uncertainty, and use the spread of the resulting forecast to characterize your predictive uncertainty. So that diagram, in that diagram, the blue wiggly lines represent the trajectory, hard to say when you're nervous, the trajectory of each model ensemble member through a massive phase space from the initial conditions through to the final forecast, and the spread of the results there gives you some idea of the accuracy of your forecast. So in other words, we're trading off some MPP scaling here for workflow scaling, because all of these extra models multiply the size of your workflow. You also have to multiply all of the tasks that surround them. Now, if you follow weather forecasting at all, you'll probably see some results from these ensemble systems around. They're pretty common now. This one shows hurricane forecast track predictions from a bunch of ensemble members. You'll also see these so-called stamp maps, which show predictions for particular forecast fields from all the members of the ensemble. In this case, it's mean sea level pressure, I think. So let's look at how this works in terms of workflow. So that is a real small regional weather forecasting workflow from NIWA from several years ago. The red nodes in the graph there represent atmospheric model runs, and the yellow ones are different observation processing tasks for different types of observations, weather observations. So that's a single. We haven't got an ensemble yet. That's one member. We still don't. That is 3 cycles of that same workflow. And you can see there are intercycle dependencies going between the cycles, which we'll come back to. So now you write your workflow in such a way that you can crank up this ensemble member number. Here it is m equals 10. It's basically multiplied the workflow by 10, including all the relevant dependencies. And for a more realistic 30 members, things are getting pretty crazy there. There's a little zoomed in view to show the kinds of systems we have to be able to handle. And this one's a global forecasting workflow from our CISE paper. And yeah, if you look carefully in there, you can see a similar ensemble structure too. So if we take a close-up of the guts of an ensemble workflow, you'll see that there are lots of there are groups of similar tasks all over the place. In this diagram, they are colored similarly. So some of those might be different instances of the model, the different model ensemble members rather, which are similar model configurations with slightly different initial conditions, and then all the tasks that follow each one of them. So to facilitate this kind of scaling, Silk has built in ways to easily and efficiently construct these kinds of workflows. We have task runtime inheritance, task parameterization, which I'll show you, and support for general Pythonic templating, which essentially lets you generate your workflow configurations programmatically. And I'm not going to show the last one in this talk. Task runtime inheritance, so that's not a dependency graph of tasks, that is an inheritance hierarchy with tasks of the leaves of this little tree. And the point is that all of the settings relevant to running a task, including what it does and where it runs and how it runs, can be inherited through a hierarchy like this, which makes it very efficient to define workflows that have a lot of common settings due to the groups of similar tasks in them. We also have this this task parameterization feature, which allows easy generation of the graphs themselves. So you can have a single workflow that will do an ensemble of any size, right down to a single member. So starting from this little linear workflow at the top of 4 tasks, we just add these 2 parameters, M, to the simulation and post-processing task, and crank that up to 5, and suddenly you get this little workflow structure. And you can have multi-dimensional parameters. So with a single line of graph configuration here and 2 parameters, I can get quite complex workflow structures like that. And just a little reminder of the point of all this, at least in the weather space. This is what came out of one of these workflows at NIWA and the unified model yesterday, in fact. So that is the atmosphere flowing over New Zealand, which is quite mesmerizing. I can sit there and watch that for a long time. Scaling a workflow engine. So I've talked a little about scaling workflows already, by which I mean if a single user wants to scale up his or her workflow, can the system handle it? So I'll say more about this soon, but let's just first take a quick detour to look at the system scaling of Silk itself at a site like NIWA. By that I mean, how can we handle many workflows for many users? We've got a couple of choices. Traditionally, in the production weather forecasting world, monolithic workflow servers were used. So that's a single server program which handles all workflows for all users. It's likely to be a massive beast of a program. It does provide centralized control, which some people very much prefer, and perhaps centralized control over security aspects too. Some people very much prefer this, but they are wrong. The way that Silk has gone is we have a bunch of distributed ad hoc servers. Basically, if you want to run a workflow as a user, you will type Silk run workflow or do it from the UI, and a server will start up to run your specific workflow running as you on your user account. So this scales sideways arbitrarily well. It provides for easy upgrades of long-running systems. You can do it one workflow at a time, upgrading Silk, that is. Simplicity, if you're a single user, you don't have to worry about the administration of this monolithic system, and a fairly low security footprint. Basic load balancing as well. So I'll just quickly show how we might deploy the system at a site like NIWA, or on the NeSI supercomputers, in fact. So that's an abstract representation of an HPC cluster. You might set aside a bunch of VMs, these blue ones, to run your Silk schedulers on. There is one running a single workflow and the red jobs that it's managing across the system. There's a whole bunch of workflows distributed across your Silk VMs. In fact, you can have triggering connections between them if you need. Another cool thing you can do, thanks to this distributed nature of the system, is if we need to take down one VM for maintenance, say, we can tell all the workflows that a particular host has been condemned, and the ones sitting on the condemned host will self-migrate to another available host. Right. Cycling workflows. So the other thing, as I said, that makes weather and similar workflows horrible, depending on how you look at it, is cycling. And this can be framed as a form of scaling too. So here's a small workflow. The red task is meant to be an atmospheric model, or any model really. Let's say you want to run this periodically to generate new forecasts every 6 hours or whatever. So 1, there's your first cycle, 2, 3, there's another one. Basically, I'm running entire cycles sequentially, and that's fine because in real-time operation, there's always a gap between cycles while you're waiting on new data. But what if you suffer a major delay and get behind the clock so that one cycle runs into the other? Well, historically, you still had to run whole cycles sequentially because systems before Silk didn't understand the inter-cycle dependencies which actually exist in these systems. And if you tried to run the next cycle early, you might violate these, bring the system down. So actually, the system looks like this. One example of those inter-cycle dependencies is that a modeled forecast will depend partly on the previous forecast for its initialization. So if you look at those cycle boxes with the cycle points labeled 1, 2, and 3, they're really an artificial constraint on the system. The individual tasks in that workflow don't care about those. They only care about their own private dependencies. So what Silk does is it sort of unwinds the cycling loop and gives each task its own cycle point label, 1, 2, 3, and so forth in the integer case here. And that creates a single, potentially infinite workflow composed of repeating tasks instead of a sequence of single cycle workflows. And how does this look at runtime? So we're zooming in on our infinite workflow here. The dark blue task represents a running task. The light blue is finished ones. And you can see the running tasks trickle through the system according to their own dependencies, regardless of cycle time. So we'll be running typically several cycles at once, dependencies allowing. 3 cycles at once there. And that can go on indefinitely. Here's another view that, of a similar system showing a job schedule. So the graph on the bottom, the horizontal bars just show length of execution for each task, and they can start when the dependencies above let them. So B and C can start after A, for instance. And here's a delay before the next cycle in real-time operation. Let's say this first cycle gets delayed by almost a whole cycle. Well, if you've got to run each task in its entirety in sequence, in this case, it takes 30 hours to catch up to normal real-time operation. The Silk way, you'll catch up pretty much immediately. The gray cases here are on time. And if you're running behind the clock entirely, such as on a historical running over historical data, you'll get that sustained high throughput the whole time. Another advantage is you can get different cycling intervals within the same workflow very easily with dependencies between them. So I thought I'd just show here how easy it is to define these cycling workflows. So here's a non-cycling one. That's a simple one-off workflow, as you can see there. The little graph R1 means run once, and A goes to B and C goes to D. It's fairly self-explanatory, and you can just see a little of how you define what each task does under the runtime section there. Now, to turn that into an infinite cycling workflow, we just add an inter-cycle dependence. I think you can see, whoa. So I'm trying to highlight some text here, but it's not quite working. Those 2 extra lines, that one says A depends on the previous A, where this is a cycle from the initial cycle point with a period of 1, and that will go on forever. So another aspect of being able to handle big workflows is program scaling. So I'll briefly touch on a few things that we found useful in terms of the efficiency of the Silk scheduler program itself, so that it can scale to handle bigger and bigger workflows. So these might loosely be grouped into memory footprint and computational efficiency, which includes language choice and use, concurrency, and algorithms. Now, Silk is written in Python, and some people think Python's too slow inherently for a program with such heavy demands on it. So let's look at this example here, a little code snippet. Computing the intersection of two sets of 100,000 members each. There's an overlap of 1,000 tasks items in the sets, foo and bar. So the sort of naive way to do it is to simply loop through the first set, and for every element, loop through the second set and see if the first element is in the second one, and add it to the intersection set. Now, if you do that, that takes 10 minutes on my laptop. And mind you, you are doing something like 10 billion conditional tests in the lower level of that loop. But if you use Python's built-in set intersection method, you immediately get a 19,000 times speed up, which is pretty impressive. So fortunately, Python library built-ins and many third-party libraries, for instance, particularly if you're doing numerical work, usually aren't written where speed matters in Python. So to avoid large amounts of computation inside, what you need to do is avoid large amounts of computation inside nested loops in your high-level Python code. And if you can avoid that, then the speed differential between Python and C, say, might hardly matter for everything else that your program does. It also pays to remember here the trade-off between high-level languages, the ease of use, and the difficulties of working with lower-level languages, which might be inherently faster. Python makes it incredibly easy, relatively speaking, to do complex things quickly and end up with maintainable code. Just out of interest, you can do this set intersection in other ways. This is a set comprehension. I for iron, foo, if iron bar is the intersection. Now that sort of looks like a fancy way of doing the nested loop, but Python clearly does something special there as well, and that's still a 14,000 times speed up. In fact, even if you do a manual loop over the top level and use a more Pythonic if iron bar test in the inner loop, even that is very fast. Here's a real world example of this, thanks to Johnny and Alex for giving me permission to use it. A tweet from Johnny Williams. An amazing hacky hour with Alex from NeSI NZ, who casually sped up my annoying slow bit of Python code by a factor of 2,000 using vectorization. So if you look at that, that is actually replacing a nested loop with a call out to NumPy, I believe, code, which will be compiled in C. It's a similar thing. Here's another amusing example. This example is so good, it's actually in the official Python documentation. So memoization is something we use in Silk quite a bit. It's automatically caching a lookup table of function arguments and results so that you can avoid recomputing results if the same arguments show up again. So it's good for small functions that get called a large number of times with the same arguments sometimes. And in Silk, we use this for vast numbers of date time computations in the cycling system, for example. We used to roll our own memoization, but now in Python 3, you can just use this thing called the LRU cache decorator, where LRU stands for least recently used cache. So this here's a small implementation of the Fibonacci sequence, which is very succinct and elegant. It just reflects the well-known definition of the Fibonacci sequence, and it's a recursive implementation. So it is simple and elegant. However, it's also the poster boy for pathological recursion, because there's 2 recursive calls inside each call. And when I run that to print the first 40 Fibonacci numbers, that takes 1 minute 15 seconds and results in 500 million function calls. But if I decorate that function with LRU, the LRU cache decorator, Python decorators are just syntactic sugar for higher order functions, a function of a function, if you like, which implements this caching mechanism, then the number of calls drops from 500 million to 40, and we get a 2,300 times speed up. So that's pretty impressive. Another thing, memory footprint. So in Python, class instance object attributes are stored in a dictionary that contains empty buckets, and that doubles in size each time it fills up to make new space. And that's what allows you to add attributes on the fly. So I've got a little cat class here, and it's got a name and a number of legs, each cat. But I can define a cat object and then add a bad attitude later on, and that's okay, thanks to this mechanism. But if you have to instantiate thousands and thousands of cats, these empty buckets in the dictionary that holds class attributes is going to hurt you. So you can define this slots thing, which sets the exact attributes that your class can hold, and then your memory use is constrained to exactly what's needed. Concurrency. In Silk, there's a lot of stuff we have to get done concurrently to avoid blocking the main scheduling algorithm, for instance. And that includes all interaction with the external world, such as job submissions and event handlers and external triggers. So let's consider a function here called task1 that takes this long to run. As it happens to do a bunch of I/O in the middle, so compute is colored and I/O is gray. Now, compute happens to be a gazillion times faster than I/O, whether it's disk or network. So your CPU is more or less sitting idle while that I/O is going on. And here's a typical synchronous program where you might be processing, say, 3 tasks in succession, one after the other. So what can you do to speed this up? There are various options in Python. Multiprocessing is a good one. That even works with, that's true parallelism. It even works with compute-bound programs. However, it only scales, we do use it in Silk, however, it only scales to the number of processors. Threading will also help a lot for IO-bound programs, but that's harder to represent in a diagram, so I'm not going there. There's a new kid on the block in Python 3, in terms of new, at least in terms of built-in language support, called asynchronous cooperative multitasking, or async IO. This is really cool. It works kind of like this. Instead of executing your task directly and deterministically, as per the synchronous paradigm on the top there, you cede control to something called an event loop, and that can start executing other tasks during asynchronous IO operations. And remarkably, because of this extreme discrepancy between IO and compute time, for IO-bound programs, this can often scale to thousands of tasks that only uses a single thread. You don't have all the complexity and danger of thread management from a user perspective. I was going to show a little example here, but I think I'm getting a little short on time, so I'll just skip over this. But it was basically to show that in Python's async IO and Python 3, for simple examples at least, it's actually rather easy to do this, and the code you write looks pretty much like the synchronous code with some bells and whistles that you do need to understand. But it's not that difficult, at least in simple examples, and it can provide amazing concurrency speedups. Now here's a big one. If your core algorithms could be much better, you might be wasting your time worrying about the speed of Python or spending loads of time optimizing your existing system. Somewhat surprisingly, we hit an example of this 10 years into the Silk project this year. So this animation shows something of how Silk 7 and earlier versions manage infinite workflows of repeating tasks. Now, here, the green tasks are running. Those are the active tasks. But if you look closely, you'll see these blue ones. The orange one is failing at repeating, but don't worry about it. The blue ones are spawned ahead before they're needed, and those are waiting tasks. And the gray ones are succeeded tasks, and they get kept around for a certain amount of time until they're no longer needed to satisfy the dependencies of the waiting tasks. So that works well. but there are some overheads to it. Basically, the scheduler needs to be aware of at least one instance of every task in the system, really multiplied by the number of cycle points you're running over. That means for a workflow with thousands of tasks per cycle, that's quite a heavy load on the scheduler. Silk 8, we implemented a new core scheduling algorithm, which we're calling Spawn on Demand, that even in an infinite workflow like this only needs to manage the current active tasks. And that's what this shows. The scheduler at any one time is only aware of these dark blue tasks, which are the active running ones in the graph. And even in a huge workflow, that might occasionally drop down to just a handful of tasks, or even one, because there's a bottleneck in the workflow, or the system's waiting on real-time data or whatever. So this can be an order of magnitude more efficient, or several orders of magnitude, even for the scheduling subsystem, if not for the whole program, and huge workflows. Another cool thing you get out of this is something called reflow. I don't think anyone else can do this. We can now have multiple wave fronts, if you like, of active tasks traveling through the infinite graph. A new front can be triggered by simply triggering the top task, and things will flow on from there. And that little animation is showing that.
You have just under 10 minutes, Hilary.
All right, thanks, Celine. I think I'll get done on time. All right, so as I said at the start, I'll spend a few minutes at the end here presenting a few thoughts and observations on issues we've faced in scaling up the Silk project, from a small one-man research toy on cycling systems to a production quality system with lots of demands on it, and a small international team working on it every day. And that's been an ongoing learning experience, to say the least. So here's a few things. First, working practices. So proper revision control and associated distributed collaborative branch and merge working practices should be a given these days. Without that, forget about it, you're screwed. Luckily, Git and GitHub and similar tools make this very easy. So we use GitHub for Silk. It's an open source project, and the GitHub flow development model is documented here on the GitHub pages. It's a lightweight branch-based workflow model, a workflow in a different sense of the word, that supports teams and projects where deployments are made regularly. It's really quite easy to understand and use. Temporal scaling. So I've been saying this, in a sense, I've been saying this a lot lately. Any non-trivial software that is still in use will never be finished, and you better get used to that idea. You know, requirements change. Users will keep pushing what they want to do with your software. Languages, libraries, packages, and tools that you depend on will continually evolve. And you'll never in a million years anticipate all of this or be able to design ahead for it all. And if you don't deal with this by resourcing your project properly, it's going to die. Managers and funders in the science world may need to be reminded of this pretty frequently, I found. You know, I presented this diagram here of changes, additions and deletions of code lines per week on the Silk project since it started in late 2008 through to today. I presented this at the first science coding conference 4 years ago, I think, and things have actually gotten cranked up again since then. There have been a staggering number of code changes over the years. This goes up to plus or minus 60K lines in some of these spikes. And the blue star far on the left amusingly shows my initial estimate of when the project will be finished. The current big example of this problem for Silk is the Python 2 end of life, which was January this year. But Silk 7, which is still our production system, is still Python 2 based. And luckily, Red Hat Enterprise Linux, for example, is still maintaining Python 2 for a while. But why haven't we finished Silk 8, which is Python 3 based yet? Well, Python 2 end of life also took out our desktop GUI, which has 2 to 3 FT of work in it, an estimate, and our stakeholders decided we should replace that with a modern web UI, and that required a complex new architecture, and that required getting recognition of the need for this and resourcing it and spinning up a bigger team to do it. So we're a bit behind the gun there. There's a preview of the amazing new Silk 8 web UI though. You'll be able to monitor and control workflows in a browser. Bruno Kinoshita will be telling you a bit about this in an upcoming Lightning talk. There's also some interesting scaling problems here, some of which impact the Silk backend. In a nutshell, I'd say if you want to display many thousands of objects in a web UI, you'd better figure out how not to have to display many thousands of objects in a web UI. That's a quick view of the Silk 8 architecture just to show you what we're up against. Don't worry about the details, but just as a rough guide, we've got distributed jobs and schedulers running on the bottom right over here, running as the user. They feeding information incrementally to a UI server, which also runs as the user. And that is spawned by a hub component, which happens to be Jupyter Hub. We're leveraging Jupyter Hub for that. It spawns Silk UI servers instead of Jupyter notebooks. And all of the workflow data ends up in your remote browser UI at the top there. So it's a big job. It's going to be really cool. Testing. Testing is another important thing we found. We wouldn't be the only ones to have found that. Testing and continuous integration are critical. You cannot change anything in a complex program without breaking something else. And only automated testing is going to reliably pick that up. So Silk has thousands of functional tests, loads of unit tests, and a growing number of integration tests. But testing is difficult, and sometimes we spend as much time trying to improve or fix the tests as we do the real code. You'll make some changes that break a lot of tests, and it's the tests that need fixing and not the code. Despite what you might have heard, how best to do this is not really a solved problem. And witness to that is this recent blog that got a lot of attention on the internet. Unit testing is overrated. So it's an ongoing, interesting problem, how to do automated testing and continuous integration properly. Second last slide, code review. That's also essential, but it's challenging. This example on the screen, the screenshot shows the scheduling algorithm change pull request that I mentioned earlier. So that was a fairly big one, plus 3,000 minus 5,000 lines of code, touched 370 files, 249 review comments that had to be addressed. That's very time consuming. Code review is actually pretty much as hard as writing the code in the first place if you do it properly, but it's not as much fun. So that's an ongoing challenge. Team size is potentially problematic too, given the scale of current development on Silk. I would say we're a little too small to be able to delegate to sub-teams, but we're big enough that the most experienced members of the team are necessarily spread a bit too thinly. Finally,
you've got about 2 minutes, Hilary.
2 minutes, great. All right, thanks, Celine. Wider uptake. So Silk has been quite successful within its home base of climate, weather, and weather-driven forecasting systems, but it hasn't seen a lot of uptake outside those areas. Now, at this point, our first priority is to continue to support those areas, of course, but we do think it might be useful to get wider uptake longer term to get more help on the project. But what are the barriers to that? Some of them are barriers of perception. I mean, Silk is incorrectly perceived to be a niche weather and HPC tool. In fact, it's just a generic workflow engine. It happens to do cycling properly, and that's necessary for those fields, but cycling could be useful elsewhere. It's perceived to be complicated and hard to use for small use cases, which isn't true, but that's just a sort of side effect of documenting all the complicated cases. It makes the user guide look big and intimidating. And we've also noticed that the cycling that Silk does is evidently hard to understand. New users often expect it to do real-time scheduling, which is a different thing entirely. So I tried to explain earlier. So those are some of the things we have to think about how to overcome if we want to get any uptake elsewhere. Silk's historical base in in-house HPC for weather prediction, of course, also means we don't really yet have cloud and container support, and new people often want that. I find that a little frustrating because it'd be very easy to bolt that onto Silk, much harder to bolt cycling onto other systems, but nevertheless, that's what people want. So we've got to address that in the near future. And those things are coming to our fields too soon. So there's luck and timing involved. And of course, Silk does have some real deficiencies like any software. So there's a lot to work on in the future if we're going to get wider uptake. Finally, thanks for listening, everyone. And thanks also to the Silk development team members and contributors, past and present. There's been about 40 contributors at this point on the project. And that's some of the current team you can see in the pictures on GitHub down below. And yeah, I really want to thank the team, because this is no longer all my work by a long shot. I couldn't do it without the others. And that's all I have. Thank you. Any questions, I'll attempt to answer them.
Thank you, Hilary. That was an awesome talk, very interesting and very enjoyable. There's quite a lot of questions. I'll start with the first one from Alex Splitzer. Do we know of applications of Silk outside of weather and climate? I think you've answered that question. It seems Silk could be a way to loosely couple multi-physics codes in general, unless there is something that precludes its use outside this domain.
No, there's really nothing that precludes that. I think if you don't need cycling, then you have a lot of other choices. So that's one thing we're up against. There are something like 200 or 300 workflow engines out there that don't do cycling, and you could spend months becoming expert in any one of them. So it really just requires someone to have a crack at it in other applications. I know that Silk would be suitable for any kind of iterative process involving iterating over application workflows, and that has actually been done, but it's still in the environmental forecasting area where that's happened. So yeah, people have used Silk. Someone was using Silk in the French Postal Service several years ago, but I haven't heard any more about that for a while. So yeah, it's a interesting question, and I think there is opportunities out there, but it needs to be explored. And there are those barriers I mentioned to getting there.
Thanks, Hilary. Another question from Cameron Keir. How much of that workflow is dedicated to QA activities?
The development workflow, I guess you mean. Well, quite a lot. I mean, I guess it depends what you mean by QA activities. I would say the automated testing is of that nature. We also have automated checking of coding style, security issues using a static code analyzer and so forth. Every commit that goes into GitHub goes through that. So, we do the best we can with our team size, and we do think that all of that's important. But I'd be interested to hear from others who have ideas about other things we should be doing on that front.
Thanks, Hilary. There's a couple of questions from Alex, but first I'm going to get everyone else a turn before coming back to Alex's questions. So one from Justin Baker. Does Silk allow you to create a visualization of the directed graphs so you can better see what your text-based schema is defining?
Yes, it does. And all of those graphs that I showed you, except for some of the animated ones, were generated by the Silk graph command, which parses your workflow definition and uses GraphViz to plot the graphs.
Thanks, Hilary. A question from James Cooper. How easy do you think it would be to change the front end from Python to another arbitrary language? I don't know of any reason to switch right now, but there could be some reason in the future.
Well, if by the front end you mean the UI, the web UI, that's of course, that has been changed. And for Silk 8, that is written in JavaScript, Vue.js, which Bruno will tell you about at some point later. As for the rest of the system, it would be a big job to change to any other language at this point, because Silk at this point is quite a substantial program with hundreds of source files, but it's possible.
Makes sense. Another question from Mike Keehan. Any comments on interactions with Slurm or other scheduling systems?
Yeah, we have built-in support for Slurm, PBS, and a bunch of batch scheduling systems used in HPC. And we can also run tasks as plain old background jobs on a host. So it's just really a small Python module that provides support for batch schedulers. And in fact, Silk submits job scripts just like a user would, but it generates them automatically. It's fairly easy to extend that to other Slurm-like resource managers if you need to.
Thanks. So now coming back to Alex, does Silk have all the expressivity of a programming language? Perform task if a condition is met. Is the Silk language Turing complete?
Cool. Thanks for that one, Alex. No. So workflows are defined in a configuration file, but we have support for several Python-like templating languages which allow you to effectively use a proper programming languages to construct your configuration file. In the future, Silk 9, we are planning to provide a Python API which will allow you to write your workflows, or at least configure them as Python programs. And then we'll be able to definitively say, yes, the Silk language is Turing complete because it's basically Python.
Thanks, Hilary. Another question from Cameron Kerr. What mechanisms are available for triggering jobs?
Well, as I showed at the start of near the start of the talk, the usual mechanism within a graph is to trigger tasks off of other tasks, and you can trigger them off all sorts of conditions on those other tasks, such as upstream task succeeded, failed, started executing, or whatever. But in addition to that, we have built-in support for triggering off tasks in other remote workflows, and we have a general external triggering mechanism so that you can provide a Python function, in fact a proper Python plugin in Silk 8 that you can write to trigger a task off any external condition that you can interrogate through your Python function.
Thanks, Hilary. We've got about 2 minutes. I've got one more question from Alexander, but just before we finish, I just want to say that the section is going to stop in 2 minutes and will be cut out. So thanks, and everyone. Thanks, Hilary, and bye if we cut out. The next session will be an hour after, actually at 2:15, between 2:15 and 3:15, and the theme will be parallel computing, Dask, and Jupyter. So it leaves 1 minute 30 to answer the next question, Hilary. Can Silk detect superfluous nodes in the graph, tasks that don't need to be executed and could be removed?
That's a yes and no. That's kind of a complicated question I can't possibly answer in the time available. It detects cyclic workflows of the bad kind and will fail those.
Fair enough.
But yeah, the rest of the question is hard to answer.
I'll just quickly check if there's any other questions, and if I got every question. I think that's all. So any last word, Hilary?
No, thanks for listening again, and thank you, Celine, for helping me out.
You're welcome. Thank you, everyone, and looking forward to seeing you on the rest of the conference. Bye, everyone.
Bye.